I want to start today with a shared trauma, really.
Oh, I think I know exactly where this is going.
Right. You know that specific frustration when you're staring at a generative AI tool?
Mid-journey, stable diffusion, whichever one you prefer.
Exactly, whatever your poison is.
Yeah.
And you have this crystal clear image in your head.
Right.
Like you want a chef.
But not just any chef.
No, you want a chef standing specifically on the left side of a chaotic kitchen, holding a spatula in their left hand.
And looking over their right shoulder.
Yes. So you type all that out, chef in kitchen, left side, holding spatula, left hand, looking right. You hit generate. And what do you actually get?
You get a chef floating in the void. Or maybe holding a spoon.
Or a whisk that merges into their arm.
My personal favorite is when the kitchen is on the left, but the chef has somehow structurally merged with the refrigerator.
Every single time. It feels like the AI is just straight up trolling you.
It gives you a beautiful image, right? Visually stunning, high resolution.
But it has completely ignored your spatial instructions. It's the text prompt lottery. You pull the lever, you get a prize, but it's rarely the specific prize you asked for.
And that's the fundamental limitation of the whole text-to-image paradigm we've been living in.
Because text is great for what, but terrible for where?
Exactly. These massive models are incredible at content. They know what a dog is, they know what a sunset looks like, but they are notoriously terrible at spatial composition.
They just don't understand where things should be.
Only what things are.
But today, we are doing a deep dive into the paper that effectively solved this.
And it really did solve it.
We are talking about ControlNet. And honestly, reading this paper from Stanford University by Zhang, Rao, and Agrawala, it feels like reading the blueprint for the next phase of AI art.
It's totally a foundational text. The full title is Adding Conditional Control to Text-to-Image Diffusion Models.
And that word conditional is doing a lot of heavy lifting there.
It is. They figured out how to stop playing the lottery and start actually directing the scene.
So the mission for this deep dive is to figure out how they did it. How do you take a model trained on billions of images?
Which is effectively a black box of genius at this point.
Right. How do you take that and force it to follow a stick figure drawing or an outline without breaking it? Because as I understand it, breaking the model was the biggest risk here.
Oh, it was the primary hurdle. To appreciate ControlNet, you have to really understand the landscape before it arrived.
It was pretty bleak for control.
It was. If you wanted to teach stable diffusion, a new trick, say, always put the subject in the bottom right corner, your options were pretty bad.
Because you can try to fine-tune the entire model.
Which means retraining the whole brain.
And that's not exactly something you do on a laptop over the weekend.
Not at all. You take this massive network with billions of parameters and try to update it with your new data. It's wildly expensive. You need a massive compute cluster. And worse, it's risky.
Risky how?
There's a phenomenon in machine learning called catastrophic forgetting.
Catastrophic forgetting. That sounds like a medical diagnosis. Like, I'm sorry, the patient has catastrophic forgetting.
In the context of AI, it's pretty much terminal. Imagine you have a brilliant artist who has studied every painting in history. They can paint anything.
Okay, I'm picturing a master painter.
Then you force them to take an intense crash course on how to draw straight lines.
Just straight lines, over and over.
Right, and they get really good at straight lines, but when you ask them to paint a face again, they look at you blankly.
Oh, wow.
They've overwritten their original knowledge to make room for the new trick.
So you gain the control, but you lose the magic. The model forgets what a dog looks like because it's too focused on where you want the dog to stand.
Precisely. And there were other attempts, right, like spatial masks or low-res, low-rank adaptation.
Which are lighter weight.
They are, but they often struggled with strict spatial control. They could change the style effectively, but telling the model, put the arm exactly here, not there, was still hit or miss.
So the Stanford team needed a way to impose strict control without giving the model a lobotomy.
Enter the ControlNet architecture.
Yeah, I looked at the diagrams in the paper, and it looks like they're cloning parts of the model.
Yes, they are using a locked-in trainable approach. This is the core innovation of the whole paper.
Break that down for me.
Imagine the stable diffusion model is a series of blocks. ControlNet keeps the original blocks locked, completely frozen.
Meaning the parameters cannot change at all.
Exactly. This preserves that genius billions of images knowledge base.
Okay, so the original brain is basically in a cryo chamber, safe and sound.
Safe and sound. But then they create a trainable copy of the encoding layers.
The parts of the model that process the input.
Right. This copy is where the new learning happens.
I use this analogy in my notes. Tell me if it holds up. Imagine the original model is the Mona Lisa.
Okay.
If I want to add a mustache or change the background, I don't want to paint directly on the canvas because I'll ruin it.
Catastrophic forgetting.
Exactly. So ControlNet is like placing a clear sheet of acetate-like tracing paper over the Mona Lisa.
Go on.
The acetate is the trainable copy. I can draw a grid, a skeleton, or a mustache on the acetate. When I look at the final image, I see the genius of the Mona Lisa underneath, but it's guided by the lines on the acetate.
That is a very strong analogy. The locked copy provides the painting skill, and the trainable copy provides the constraint.
The original painting is never touched, but the result is a composite of both.
Yes, but there's a massive engineering challenge your analogy glosses over a bit.
Lay it on me.
In the physical world, acetate just sits on top of a painting. In a neural network, these two layers, the locked one and the trainable one, have to mathematically talk to each other.
They have to pass data back and forth.
They do. And this is where the paper gets pretty heavy with the math. They introduce the concept of zero convolutions.
Yes, the zero convolutions. This felt like the secret sauce.
It is absolutely the secret sauce.
Okay, I need you to walk me through this part. Because a convolution is just a math operation, right? A filter.
Simply put, yes.
But if it's a zero convolution, doesn't that mean the weights, the numbers that determine what the filter does, are set to zero?
That is exactly what it means. It is a one-by-one convolution layer where the weights and the bias are initialized to zero.
But wait, basic math here. If I take a signal from my trainable copy and I multiply it by 0, the result is 0.
Correct.
So if the output is 0, aren't we just adding nothing? How does the model learn if the new layer is essentially turned off?
And that is the aha moment of the whole architecture. You have to think about the very first step of training. Step 0.
Okay, step 0.
You have your locked model, which works perfectly. You have your new trainable copy, which has learned nothing yet. It's full of random noise or unhelpful data.
Right.
If you let that new copy scream its random noise into the locked model, you'd create chaos. You'd get garbage output.
So the zero convolution is like a noise gate.
Exactly. At the start, the zero convolution outputs 0. Mathematically, the equation is just y equals y plus 0.
So the model behaves exactly like the original stable diffusion.
It's a perfectly safe starting point. But, and here's why your question about learning is important, even though the output is 0, the gradient is not 0.
The gradient being the signal that tells the model how to learn.
Right. As soon as you show the model a training image, say, a Canny edge map of a dog, and the model compares its output to the real image, it realizes there's a difference.
It calculates an error.
Yes, that error signal flows backward through the network, back propagation. Even though the weight started at 0, the math dictates that they should shift away from 0 to reduce the error.
So it starts at 0 to play it safe. It's effectively whispering, I have nothing to add yet.
Yes.
But the moment training begins, the math says, hey, if you nudge this number from 0 to 0.001, the picture would look better.
Precisely. It allows the control signal to grow organically. It prevents that harmful noise from breaking the deep features of the backbone right at the start.
It's a graceful on-ramp for the new data.
A very graceful on-ramp.
That explains a really weird graph I saw in the paper. Figure 4. They call it the sudden convergence.
Yes. This is fascinating behavior to watch during training.
Because of the zero convolutions, right?
Right. For the first few thousand steps of training, the error rate barely moves. The model is effectively ignoring the control input because the weights are still close to 0.
So it's just generating images based on the text, completely ignoring the lines you gave it.
Exactly. If you were watching the training, you might think it was broken. Why isn't it listening to me?
Right.
But then, in one experiment mentioned in the paper, around step 6133, something incredible happens.
The model snaps.
It snaps. The error rate plummets like a stone. The model suddenly converges.
It goes from ignoring the condition to following it perfectly in a very short window.
It's not a slow, gradual learning curve like we usually see in AI. It's a sudden realization, oh, these lines match the image structure.
It's like when you're staring at one of those Magic Eye posters and suddenly the 3D image pops out. It's all or nothing.
That's a great way to visualize it. And there's another counterintuitive trick they use to make this happen faster. During training, they randomly deleted the text prompts.
I saw that. 50% of the time, they replaced the text prompt with an empty string.
Yeah.
That seems backwards.
Huh?
If I want to train the model to generate a cyberpunk deer, don't I need to tell it this is a cyberpunk deer?
You do, but if you always tell it this is a cyberpunk deer, The model gets lazy.
Oh, it relies entirely on the text to know what the object is.
Exactly. It looks at the word deer and draws a deer. It might just ignore the squiggly lines you provided as the control because the text is easier to understand.
I see. So by deleting the text, you're forcing the model to play detective.
You give it the squiggly lines, the edge map, and no text. The model has to look at the lines and figure out, okay, judging by this shape, this must be a deer.
It forces the model to learn the semantics of the visual input, not just the text input.
Which strengthens the connection between the acetate layer and the painting layer.
That makes total sense. Now, we've been talking about squiggly lines, but the paper gets very specific about what kind of controls this thing can handle. They didn't just build this for one thing.
No, they tested it on a wide variety of conditions, and some of these terms might be familiar to photographers or 3D artists, but they're definitely worth defining.
Let's run through them. The first one is Canny edges.
Canny is a classic computer vision algorithm from the 80s. It basically looks at an image and detects sharp changes in contrast.
So it turns a photo into a simple drawing of white outlines on a black background.
Exactly.
And the results in Figure 1 are wild. They take a canny map of a deer, just the outline, and generate a cinematic version, a winter version, and a fairy tale version.
And the lighting changes, the texture changes.
But the antlers are in the exact same pixels across all the images.
That's the lock working. It's brilliant. Then you have heat lines.
Hoof! Is that geometry class coming back to haunt me?
A little bit. The Hoe transform is a technique for detecting straight lines. This is incredibly useful for architecture.
Because buildings have hard edges.
Right. If you have a photo of a room or a building, Hough lines capture the perspective, the vanishing points, the rigid structure.
So I could sketch a rudimentary boxy building, and ControlNet locks onto those perspective lines and turns it into a sci-fi skyscraper or a Gothic cathedral.
Yes, but the geometry remains perfect. It separates the structure from the style.
That's incredible. What about normal maps? Gamers will probably know this one. It's those weird purple and blue images, right?
Correct. A normal map tells the computer the orientation of a surface, which way it's facing in 3D space. Is it curving left? Is it flat?
This provides incredible control over lighting and 3D form.
It does. And there's a slightly creepy example in the paper using a statue.
The Lincoln Memorial.
Yes, they took a photo of the Lincoln statue, generated a depth map.
Which shows how far away every pixel is from the camera.
Exactly. And then they told the AI to turn it into a real man.
And because the depth map preserved the 3D folds of the clothes and the facial structure, it didn't just paste a face on.
No, it turned the stone into flesh.
It looked like Abraham Lincoln was sitting in that chair, breathing. It preserved the geometry while completely hallucinating the material.
It's reskinning reality.
But my absolute favorite has to be open pose.
The human pose control.
This solves the floating chef problem we started with. Open pose turns a human body into a stick figure, a skeleton.
Red line for the arm, blue line for the leg.
Right, and ControlNet can take that skeleton and wrap any character around it.
You can take a photo of yourself doing a kung fu kick, extract the skeleton, and generate a monk, a robot, or a chef doing that exact same kick.
This is huge for storyboarding. You can keep a character consistent in their movement across different panels.
It creates consistency, which has essentially been the holy grail of Gen AI.
But here's the thing that usually kills the vibe with these papers.
The compute costs.
Always. Usually you read about this amazing tech, and then you scroll down to the experiment section and realize they trained it on a supercomputer that costs more than my house.
But that is the best part of this paper, the efficiency.
Lay it on me. What kind of hardware do I actually need?
They trained the ControlNet for depth-to-image conditioning on a single NVIDIA RTX 3090 Ti.
A 3090 Ti. It's a nice graphics card, but that's a consumer card.
It is.
That's something a high-end gamer has in their PC. It's not a data center.
Exactly. Compare that to the original training of Stable Diffusion, which required clusters of thousands of A100 GPUs burning electricity for months.
Wow.
ControlNet is basically a sidecar to the main model, so you only have to train the sidecar. The heavy lifting, the billions of parameters in the main model, is already done and locked.
And what about data? Don't I need millions of images of turtles to teach it to control a turtle drawing?
This is perhaps the most disruptive finding in the whole paper. ControlNet works with small data.
How small?
They performed an experiment where they trained a ControlNet on just 1,000 images.
1,000. That's a folder on my desktop. That's nothing in the world of big data.
They used 1,000 images of a lion, and the model didn't collapse.
No way.
It learned to generate a recognizable line controlled by edges. This is a massive shift. It means you don't need to be Google or OpenAI to build a tool.
So a shoe company could take 1,000 photos of their latest sneaker, train a ControlNet on just that silhouette, and suddenly they have an AI tool that generates their specific shoe in any environment.
Yes. It democratizes the creation of the model itself, not just the image. It moves us from general purpose AI to bespoke AI that runs on your home computer.
That is a wild implication. We've gone from the text prompt lottery to a precision design tool pretty fast.
Very fast.
But I want to push on the capabilities a bit more. We talk about the empty text prompts during training. Does that feature actually show up in the final product?
It does. It leads to a feature they call guess mode.
Guess mode. It sounds like a game show.
It's surprisingly powerful. Because the model was forced to learn visual semantics during training, you can actually remove the text prompt entirely during generation.
So no prompt at all.
Right. You can feed it a scribble of a house, type nothing, and the ControlNet will analyze the lines and say, I see a roof, I see windows, I'm going to generate a house.
It have intuition?
It has visual understanding. It interprets the intent of the sketch. It meets you halfway.
And can you stack these? Like, can I have the pose control for the character and the depth control for the background at the exact same time? Or is it strictly one at a time?
Oh, you can stack them. It's called multi-ControlNet.
Really?
Because these are just additive layers. Remember, they start at 0 and add to the signal. You can run a pose ControlNet and a depth ControlNet simultaneously.
So I can say, put the astronaut here using pose, in a room shaped like this using depth, looking like this using Canny.
Exactly. You are no longer asking the AI for a favor. You are engineering the image.
This feels like the bridge between prompt engineering and, I don't know, visual engineering.
I think directing is the right word. Before ControlNet, using GenAI was like describing a dream to a sketch artist over the phone.
No. Make the nose bigger? No, not that big.
Right. With ControlNet, you are grabbing the pencil. You are defining the structure like an engineer, using edge maps and skeletons, and letting the AI handle the rendering like an artist.
It shifts the skill set completely. And that leads me to a thought I had while reading the intro. The authors talk about flashes of visual inspiration. They mention that these flashes are often fleeting and hard to put into words.
Right. A chef in a kitchen is a very low-resolution description of a high-resolution idea in your head.
But now, if I can scribble a terrible stick figure or trace a stock photo, I can execute that high-resolution vision perfectly.
You can.
So here is the provocative question I want to leave everyone with.
Let's hear it.
If the barrier to entry for professional-grade composition, lighting, and structure has effectively dissolved, if a messy scribble can become a masterpiece thanks to ControlNet, what does skill actually look like now?
That is the question of the decade. I think skill stops being about the mechanical execution, the ability to draw a straight line or shade a sphere perfectly. The AI does that better.
It's already solved.
Right. Skill becomes about the vision itself, the composition, the storytelling. The AI can render the perfect lighting, but you still have to decide where the light comes from.
The tool is only as good as the hand holding it, or in this case, the hand sketching the stick figure.
Well put. The floor has been raised, but the ceiling is still entirely up to you.
We've put links to the paper, and specifically those images of the winter deer and the Lincoln statue in the show notes. You really have to see the visual consistency for yourself to believe it.
Highly recommended. It's one thing to hear about it, but it's another to see the locked nature of the control in action.
Thanks for diving in with us. Go draw some stick figures and see if you can turn them into masterpieces. Catch you on the next deep dive.